In this video, we're going to solve a problem that contains a piston cylinder, but this time it contains two sets of stops instead of one, like the last problem we did. We are going to solve for the amount of work that the water does on the piston, and on my next video, we are going to solve for the amount of heat that is added to the water. So let's go ahead and begin. 1 kilogram of water is contained in a piston cylinder device at 100 degrees Celsius. The piston rests on lower stops such that the volume occupied by the water is 0.1835 meters cubed. The cylinder is fitted with an upper set of stops. When the piston rests against the upper stops, the volume enclosed by the piston cylinder device is 0.841 meters cubed. A pressure of 200 kilopascals is required to support the piston. Heat is added to the water until the water exists as a saturated vapor. How much work does the water do on the piston? Alright, so we are going to go ahead and find the amount of work that the water does on the piston. We're not going to concentrate on the amount of heat added. And usually for a closed system of a piston cylinder, our work equation is as follows. Integral of P dV, which ends up being P times V final minus V initial. Perfect. We know that initially the device is at 100 degrees Celsius, and when the piston rests on the lower set of stops, the volume of the water is 0.835 meters cubed, so that's going to be our first state. What else do we know? We know that when it hits the upper set of stops, the volume of the water is 0.841 meters cubed. We also know, this is really important, the pressure required for the piston to move is 200 kilopascals. So that's how much pressure it needs to move. And what else do we know? I think that's pretty much it. Oh, and we also know that our final state is going to be a saturated vapor. So perfect. Final state, saturated vapor. Perfect. Let's go ahead and figure out our different states, or how many different states we have. So I know that our first state in this problem is going to be right here, when the piston rests on the first set of stops. We know that the mass is going to be 1 kilogram because it says so in the problem statement. And it's going to be 1 kilogram for all the other states because it is a closed system. There's no mass coming in or out of the boundary, or in or out of the piston cylinder. We know that our initial volume is 0.835 meters cubed. And we also know that our initial temperature is 100 degrees Celsius. In order to figure out the state of our water, we usually need two different properties that we can find in our steam tables or saturated water tables, because since we have water, we're able to do that, and we have those tables in the back of our textbook. So we're going to need either temperature and pressure, or temperature and our specific volume. It really just depends on what you have. Here in our problem, they don't give the specific volume. They give us volume and mass. But we're able to find specific volume because specific volume is equal to the volume divided by mass. Great. So our specific volume is going to be 0.835 meters cubed per kilogram, because 0.835 meters cubed is our volume divided by 1 kilogram. So 0.835 meters cubed per kilogram. Alrighty, perfect. So we're going to go ahead and find state 1. by using our temperature and our specific volume. So we're going to go ahead and look up the temperature at 100 degrees Celsius at our saturated liquid vapor mixture table in the back of our textbook. And we see here that at 100 degrees Celsius, the specific volume of a saturated liquid is going to be this guy right here, 0.001044. The specific volume for a liquid vapor is 0.167185. And the specific volume for a saturated vapor is 1.6729. Alrighty, so if the specific volume that we have is between these two guys right here, then that means we have a saturated mixture. If it's exactly 0.001044, it means it's a saturated liquid, and if it's exactly 1.67290, it means that it's a saturated vapor. And if it's less than our saturated or specific saturated volume of a liquid being 0.001044, if it's lower than that number, it means it's a compressed liquid. So it's on the left side of the dome, it's completely liquid. And if it's greater than our specific volume of a saturated vapor value of 1.67290, if it's greater than that number, it means it's a superheated vapor, so to the right of the dome. So let's go ahead and compare. Our specific volume is 0.835 meters cubed per kilogram. And if we check our table, that means, so let's go ahead and just re-explain that, right? Our specific volume of a saturated liquid is 0.001044. The specific volume of the saturated vapor is 1.67290. And again, this is when the temperature is 100 degrees Celsius, right? And our specific volume is 0.835. Our specific volume lands in between these two. So that means that it is a saturated mixture, right? It's under the dome if we were to draw our PV diagram. So for our first state, it's going to be a saturated mixture. Saturated mixture, right? Perfect. And if we know that it's a saturated mixture, that means that we also know that our pressure is 101.3, because these values are for saturated mixtures for water, right? So our P1 is going to be 101.3 kilopascals. I don't know if it's going to be important yet. We'll see later on in the problem if we need that. Alrighty, perfect. Now our second state is going to be like this. Our second state is when the piston is about to start moving. It's still on the first set of stops, but it's the millisecond before it starts moving. So we know that the mass is still 1 kilogram, right? Because it's a closed system. The volume is still 0.835 meters cubed, right? Because it's still on the first set of stops. However, the pressure is not the same. The pressure is not 101.3 kilopascals. The pressure is going to be 200 kilopascals, because that's the amount of pressure for the piston to start moving. And that's the state that we are in right now, in state 2. Alrighty. We need to go ahead and figure out whether this is a saturated mixture, whether it's superheated, whether it's somehow turned into a compressed liquid. And we do that by having two properties that we can find in our table. And so we either need temperature, pressure, or a specific volume, right? In this case. Later on, you'll learn about enthalpy, entropy, and internal energy. But right now, we either need temperature, pressure, specific volume. One of those two two of those three, right? So we have pressure, we don't have specific volume, but we can find specific volume because specific volume is volume divided by our mass, which we can easily do. So we know that our specific volume is going to be 0.835 meters cubed per kilogram. Perfect, not too bad. So now we do the same exact thing we did for state 1. We're going to do with state 2. We're going to go ahead and compare the specific volume to the values that we find when the pressure is 200 kilopascals. So let's go ahead and look at state 2. So now we're going to find state 2. Find state 2. We're going to, here, let's write that up here. Find state 2. We're going to look up P2 equal to 200 kilopascals and compare our V2. Compare. And this table is table 5.2 in my textbook, properties of saturated water. And this one is the one with the pressure. All right, so pressure, we find it 200 kilopascals. Great. And now we're going to go ahead and compare these two values with our specific volume. So let's go ahead and do that. So the specific volume when it's a saturated liquid is 0.001061, and the value when it's a saturated vapor, it's 0.88573. Great. And ours is 0.835. So again, same thing. If it's in between those two numbers, it's a saturated mixture. If it's less than the specific volume of the saturated liquid, if it's less than that, it's a liquid. And if it's more than the specific volume of a saturated vapor, then it's superheated, right? So in this case, as well as in the last state, our specific volume is in between the specific volume of saturated liquid and the specific volume of a saturated vapor. So again, that means saturated mixture. So saturated mixture for state 2. And since it's saturated mixture, we can go ahead and use the value right here for the temperature. I use the same the same value, so 120.23 degrees Celsius, I believe. And that's what I get for taking off the units. But I'm pretty sure, yes. Temperature is 120.23 degrees Celsius. Perfect. Now, what should we do? Now let's go ahead and look at state 3. So at state 3, so for state 3, let's go ahead and assume that it's at the stops. Let's say that with the amount of heat added, it turned into a saturated vapor, and it was a saturated vapor when it hit the stops, or it turned into a saturated vapor when the piston has been on the stops, right? So let's go ahead and figure that out. Let's figure out if that actually happened. So let's assume that it did, and let's check the values, and that's how we're going to be able to figure out if it happened or not. So bear with me while we do this. So we're going to go ahead and assume that it made it to the stops. So the mass is still 1 kilogram, right, because closed system. The pressure is still going to be 200 kilopascals because that's when it barely touched the second set of stops. Barely touched it. It's about to touch it. So it's still 200 kilopascals because when you have a floating piston, or when the piston is moving at a constant velocity, then the pressure is still the same. So your pressure is still going to be 200 kilopascals. Great. I know this is new for you guys, but you're going to have to get used to it. When it's floating, or when it's barely about to start moving, or when it's barely about to reach the set of stops, it's still going to be the pressure that the problem statement said it's going to need in order for it to move. Alrighty, moving on. And we also know that the volume is going to be 0.841 meters cubed, as stated in our problem statement. And again, we're not given, in order to figure out the phase of state 3, we need 2 of either the specific volume, pressure, or temperature. We're only given pressure, but we're able to find specific volume because, again, specific volume is volume over mass. So our specific volume for state 3 is going to be 0.841 meters cubed per kilogram. Great. Moving on. Let's go ahead and find the state of, or the phase of state 3. So find state 3. So we're going to go ahead and find state 3 if at stops. Right, because right now we're assuming that it made it to stops, because it might have not made it to the stops. But let's assume that it did. So we're going to go ahead and we're going to look up P3 is equal to 200 kilopascals and compare the same thing we've been doing, and compare the specific volume with the specific volume of a saturated liquid and the specific volume of a saturated vapor at a pressure of 200 kilopascals in table 5.2, properties of saturated water. That's the table that's the name of the table that I use in my textbook. I don't know, your textbook, you're going to have to figure that out. Alright, so we're going to look up pressure 200 kilopascals, same as in state 2, and I see that our specific volume for saturated liquid is 0.001061, and our specific volume of a saturated vapor is 0.88573. Alrighty, so I'm just going to go ahead and write it over here to keep myself organized. 0.00 like this, and then saturated vapor 0.88573, and our specific volume is what was it? It was 0.841. Our specific volume is in between the specific volume of a saturated liquid and the specific volume of a saturated vapor, meaning that it's still a saturated mixture. Okay. So in state 3, still a saturated mixture. Okay. Our final state is when the water is, what did it tell us? Final state is when the water is a saturated vapor. Okay? So we started with our state 1, right? Piston's not moving. Piston is still in a set of stops. And then we go into phase 2. In order to go into phase 2, we added some heat, right? In phase 2, the piston is still not moving, but it's about to move because the pressure reached 200 kilopascals, right? Because we added some heat. And then from state 2, we added even more heat so that it moved all the way up to where the top set of stops are. And when we added an X amount of heat that I'm not sure of yet, we'll find out in our next video, when we added that amount of heat, it lifted our piston up to the second set of stops. But when we added that heat, it wasn't enough for it to turn into a saturated vapor. It was enough for it to still be saturated mixture. So we need to figure out, again, what amount of heat it will take for this saturated mixture at the set of stops to turn into a saturated vapor. Okay, meaning we have a fourth state in this problem. So we have a fourth, we have another state in this problem. Right? We're not going to figure out how much heat we added in this problem. We'll figure it out in our next problem, in our next video, but we still need to know what this fourth phase is, how it looks like, in order to figure out work and such. Actually, we don't, but it's still important to know. So let's continue. So in this fourth state, right, still looks exactly the same as our third state, right? Because our piston is still at the second set of stops, right? But it's not a saturated mixture. We know that it's going to be a saturated vapor. We know that the mass is still 1 kilogram because our piston is it's a closed system, right? Nothing's going in or out of the piston cylinder. We don't know what the pressure is, right? Because it's not 200 kilopascals, because 200 kilopascal is when it's moving. And in this, when it's already on the set of stops, it's not moving anymore. The pressure is increasing, right? Because we're adding heat. And since we're adding heat, water wants to expand, but it's not, the piston is not letting it expand. The stops is not letting it expand, right? So pressure is increasing inside of our piston cylinder. So we don't know pressure just yet. What else should we or do we know? We know that the volume is still 0.841 meters cubed because our problem doesn't say anything about the piston cylinder breaking or removing the second set of stops, right? So our final volume, or our volume of the fourth state, is still going to be 0.841 meters cubed, meaning that we know that our specific volume is 0.841 meters cubed per kilogram, because specific volume is volume divided by mass. Perfect. Now, we can go ahead and find pressure and stuff because we know it's a saturated vapor. So let's see. Should we even do that? I'll spare you that. We'll figure that out maybe in our next video. But as of right now, let's go ahead and try finding work. So work is pressure times the final volume minus the initial volume, right? So let's go ahead and write that down. Again, work is PdV. P is initial times V final minus V initial. Great. And friendly reminder, just in case you don't remember, work happens when piston moves. Alrighty, so from state 1 to state 2, let's go ahead and look at our beautiful pictures that we drew, or drawings that we drew. State 1 is state 2. Does the piston move? No, did not move. It is still on the first set of stops. Therefore, there is no work from state 1 to state 2. Let's go ahead and check out state 2 to state 3. Does the piston move from state 2 to state 3? Of course. Yes, it moved from the bottom set of stops to the top set of stops. So we know that from state 2 to state 3, we have work because the piston moved. Now let's go ahead and check out from state 3 to state 4. State 3 to state 4. Did the piston move? No. Some heat was added, right? However, just because heat was added does not mean that there is work. Heat was added, but the piston did not move from state 3 to state 4. It's still on the top set of stops. So no work. No work from state 3 to state 4. Alright. So work is equal to P times our final volume, right? But final volume of when work is actually happening. Work is actually happening. So final volume will be our volume of the third state, right? Because that's when work happened. Minus a volume of initial, right? But the volume initial when work is about to happen, right? So V2. Because work did not happen from state 1 to state 2 or from state 3 to state 4. It happened from state 2 to state 3. So that's where we use volume initial and volume. That's where we get volume initial and volume final from. So we'll go ahead and calculate that. So work is equal to 200 kilopascals, right? Because this is going to be pressure per initial pressure. So in state 2, which is our initial state, the pressure is 200 kilopascals. So that's why pressure is equal to 200 kilopascals times volume of state 3. Volume of state 3 is 0.841 meters cubed. 0.841 minus volume of state 2, which is 0.835. And all of these are meters cubed. We do the calculations, and we get that work is 1.2 kilopascals times meters cubed. And in case you guys have forgotten, 1 kilopascal meters cubed is equal to 1 kilojoule. So the amount of work that the water did in this problem is 1.2 kilojoules worth of work. So that would be the answer for this problem. In our next video, we're going to learn, or we're going to find out the amount of heat added into the system, right? So we're going to go ahead and find that Q, and that Q. And for that, we're going to need the first law of thermodynamics for a closed system. But that's it for this video. I hoped you learned something. Good luck with your studies.